Previously, you should have learned how Thomson was able to show that the charge to mass ratio of cathode rays was much higher than that of hydrogen atoms, and so he was able to suggest that the rays were much less massive. The cathode rays were considered a stream of particles, which we now know as electrons. However, the actual charge of electrons could not be determined since the mass was unknown. Several unsuccessful attempts were made to determine the charge of an electron until Robert Millikan came up with a plan. A tiny drop of oil was sprayed into the space between two charged plates. The oil drops would become charged as they left the sprayer, so the electric field would push them up. At the same time, gravity would pull the drops downward. If the drops remained floating in the chamber, then these two forces were balanced. By carefully measuring the size of the oil drop with a microscope, Millikan could calculate its volume. Since he knew the density of the oil, he then knew the mass of the oil drop, and hence its weight, or the force it was being pulled down with by gravity. He could then divide this force by the electric field strength to determine the charge on the oil drop. This charge would vary depending on how many electrons had caused the charge. It is worth mentioning this is a slightly simplified version of the method, since Millikan also had to account for air resistance and buoyancy in his calculations. However, it doesn't affect the overall conclusion. The simulation from Physics Aviary lets you follow a similar method to Millikan. Start by clicking on the bulb on the left to spray some oil. A drop has remained floating, so click on the microscope on the right to measure the size of the drop. The drop appears to have a radius of 500 nanometers. Note that the potential difference between the plates is 12.7 volts. Record the voltage and radius, then repeat the experiment until you have at least 10 sets of data. Don't worry if you get different voltages for similar sized drops. It's simply due to a different amount of charge on the drops. Once you have your data, it's time to analyze it. The first step is to work out the volume of each drop. The volume of a sphere is 4/3 pi r cubed. Enter that in, being careful to convert the radius to meters. To find the mass of the drop, multiply the volume of the drop by the density of the oil, 900 kilograms per cubic meter. To find the force due to gravity, multiply the mass of the drop by 9.8 meters per second squared. To calculate the electric field strength, divide the voltage by the separation between the plates, 3 millimeters. Since the upward force due to the electric field is equal to the weight, divide the weight force you calculated by the electric field strength to find the charge on the drop. Use Excel to repeat this process for all of your data. Note that the charges do vary, but they're all around 10 to the minus 19 or 10 to the minus 18 coulombs. Sort the data so that the charges are in increasing order. Then subtract each one from the previous to find the difference between them. To find a more accurate estimate of the charge on an electron, you need to take into account the error in the radius measurements. These could vary by about plus or minus 5 nanometers. To find the minimum charge, repeat the previous calculations, but subtract 5 from the radius. Again, to find the maximum charge, add 5 to the radius. Enter a test value for the charge of an electron in a cell. In this case, 1.5 times 10 to the minus 19 has been entered into cell I15. To determine how many electrons have been added, divide the charge in each row by the test value. Use the dollar signs in your formula to lock the cell reference. Repeat this for the minimum and maximum charges. Now fill down. Note that the minimum value is greater than 1 in these data. Try a slightly greater test charge. Keep fine-tuning until you are satisfied that you have a reasonable approximation. Millikan repeated this experiment many times and found that the charge on the trop varied quite a bit, but would be integer multiples of a very small charge of just under 1.6 by 10 to the minus 19 coulombs. As more investigations were performed by other parties and new methods were found, the current value was eventually determined.